All right, so let's go on. So we had already finished this reaction. Account for the fact that dehydration of CH3, CH2, CH2, CH2OH yields mainly. So let's write this. How many carbons are here? I'll start from where the hydroxide is. One. Let me change the color here. This is one carbon, two, three, four. So I've got four carbons. One, two, three, four. At the end, I've got OH. So they have said that the dehydrogenation of this one, okay, the removal of dehydration actually, the removal of water. So we're removing water from this reaction. It's going to form this guy. One, two, three, four, which has got a double bond on the middle, rather than this guy which has got a double bond at the end. Why is it going to be so? So in a dehydration reaction, so account for that fact. So step one, because when you're accounting in chemistry, we want to use a mechanism. So when you react an acid with an alcohol, you form an alkene. Just like when you react an alkene with an acid, you form an alcohol. But the only difference is that we increase the strength of the acid if we want to move from alcohol to alkene. Because when we are doing it the other way around, we use more of the water. Am I, uh, am I making sense? Okay. So when you are converting a double bond to an alcohol, you use sulfuric acid, but it should be dilute, and a lot of water should be dilute. If you want to go the other way around, you need to increase the concentration of the sulfuric acid and use less water. So it should be concentrated sulfuric acid to go in the reverse reaction. So what we are going to be able to see is that oxygen act as a nucleophile. It grabs the proton here, breaking off this bond. So we form oxygen that is protonated. The main reason for doing this is just want to make, by the way, what I've written here is not something with four carbons. So I need to put four carbons. One, two, three, four. So I wrote something with three carbons. Okay, the main reason as to why we are forming H2O plus is because it's a good living group. And this guy can live. Okay, this guy can live like that. And then what we'll be able to see is that, so because it has lived, this carbon will remain positively charged. Now, a primary carbon is not stable. So what happens is that the hydrogen can move from here and it comes at this end. That is a hydride shift. Where the hydrogen is going, the positive charge is going to move out. So it will now come here. Okay. And then in the second step, that will be step two, this positive charge is going to be able to. So you look at where, when you every time you are forming alkene, just look at one step away from where the positive charge is. Like for example, here there's a hydrogen. Okay, your acid, the thing that you formed from the acid, that conjugate base here, is going to come and grab this proton. That will break off this bond, and that is going to form this thing. Now this is going to be the minor product because it is being formed from something a primary carbocation which is not stable. The other thing that can happen is that you can now get the secondary carbocation. Now for this one, you can grab a hydrogen one carbon away from where the positive charge is. You can grab either here or here. But then if you grab here, you form the same product as the one you formed here. So we're going to grab a proton from the other end. We're going to grab it here. So the conjugate base also still comes in to come and grab this. That will break this bond. And this is going to be the major product because it is formed from major carbocation. Just make sure that you say some English after you write the mechanism, because they'll not just make the mechanism, they are saying account for. So speak some English there. Because of the secondary carbocation which stability, it forms a more it forms a major product. Is this okay? Okay. Let's look at this one. Predict the product as major, minor. Yes. Okay. Predict the products as major, minor, or the only product. Start the mechanism as state the mechanism as E1, SN2, SN1, E2 for each product. So I'm starting with 3-chloropentane. 3-chloropentane. Okay. The structure is a pentane, it's like that. 5 carbons. One, two, three, four, 5. At position number 3, it has got a chlorine. Okay. So I can put a chlorine here. This one is reacting methoxide. Methoxide, I can also write it like so. Basically, oxygen bonded to a methyl group. So factors that promote what? So let's talk about them as a summary. When you have got a primary substrate, okay, primary substrate, secondary substrate, tertiary substrate. A primary substrate, when you are using a strong base that is unhindered, and then it is also at high temperature. Why am I writing 50? Supposed to say high temperature, I'm writing 50. So whatsoever high temperature, okay, you are using heat. How do you know that a substrate is unhindered? If it doesn't have a lot of ara groups. How do you know that it's strong? Mostly those which are strong are going to have more electronegative atoms to them. Okay. So if the substrate is primary and then all these conditions have been met, the reaction is going to go more by SN2. Major product will be by SN2. The minor product is going to be by E2. Now, if you use the same properties here, but then you use a secondary substrate, you are just going to reverse. The major product will be by E2, the minor will be by SN2. When you use a tertiary substrate do not form by SN2. Instead, the reaction will be more by either E1 or E2. It will happen a little by SN1. If you increase the temperature, high temperature promotes elimination reactions. So if you increase temperature, you will not even form anything by SN1. Now, so there will be a competition between E1 and E2. If you use something that is bulky, if you use a bulky base, a bulk nucleophile, that will all, go more by E1 because it's bulk for it to go and attack, to go and grab and like that. Okay, so take note of that. Is that okay? If you know that, it will be very easy. Is that good? The more we take time to respond, the more I wait. Yes, please. Okay, for example, you can have a strong compound but it's bulky. Strong nucleophiles, I said, mostly are going to have more electronegative atoms like oxygen, like nitrogen, those guys. So let's say, for example, I've got this guy, oxygen, but it is attached to 4 other carbons. This is a tet butoxide. Tet butoxide is a very strong base. because of the oxygen there. So if you have something in this form, ara can be anything. These are strong bases, but then it is hindered because it has got a lot of methyls. So that is an example that we can give. Is that okay, Doc? Okay. So now let's determine. This is a secondary substrate. The base is strong. We can see it is oxygen bonded to CH3 and it is unhindered. And then you can see this is high temperature. This reaction is going to go by what? What will be the major mechanism? What will be the major one? I shouldn't have written what I've written here. Even after writing, we can't speak. Okay, the others I'll keep them to myself since we don't want to. We want me to talk alone. So this reaction, ah, but it's better you speak. It will make a difference other than me talking alone. Okay, so look at this. This is secondary substrate. The base is a strong base and it is unhindered and there is heat. Yes, thank you very much. So the major product is going to be by A2. Okay, so we'll write something by A2. Now E2, remember every time I'm talking about elimination, you form double bonds. So where you have got your halogen, grab a proton one step away. So you can grab a proton here or you can grab a proton here. Say same, you form the same product. When you grab this proton, you break this bond to form a double bond, and that will make this guy to leave. So this will be the major product, and it's by A2. Okay. The minor product is going to happen by SN2. I'll use the same one. But the minor which is going by SN2, what will happen is that this guy, the same nucleophile, will attack from the back. When it attacks from the back, then this guy, the chlorine, is going to leave. So what you'll be able to see is going to be something like this. We no longer have the chlorine there. Instead, we are going to have this oxygen with CH3 as bound there. So we end up forming an ether. So this is the minor product. Is that okay? Okay. So for the second one, it's the same structure that we were given on top. 5 carbons. At position number 3, we still have the chlorine. But then we are using CH3COO. So this is, uh, how do I even write it? Okay, I've got a carbon double bond, oxygen like that. Okay, this is the one. This guy is coming from acetic acid. Are we able to see my board? Oh, okay. I thought it's not. Okay, you can see the conditions are basically the same. The only thing that we have changed, also the temperature is the same. We have only changed from methoxide, now we are using this guy. Let's predict. What do you think will be the major product? Okay, so I want someone to tell me what we have as the uh, substrate. Is it primary, secondary, tertiary? The 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 base also, if it is strong or weak, and then also the temperature. Comment also on the temperature, and then also comment if it's bulk or not. Anyone to comment on that? Okay. Uh-huh. Please uh, go on. Am I the only one who can't hear, or a bulk base? Okay. Thank you. Is there any other suggestion? Any other suggestion? All right. So if you look at this base, it's really not really that weak. Sorry, it's a strong nucleophile. It's a strong nucleophile because we're having oxygen bonded to some other group. But then this guy is a weak base. Okay, it's a weak base. Why are we saying it's a weak base? It's formed from a strong acid. Acetic acid is a very strong acid. And you know that the opposite happens if you add a strong acid, the base that is going to be produced is going to be a weak one. It is a bit of hindered, right? A bit of hindered. So already we know that the mechanism by which it should go is supposed to be more of the E2 and the SN2. Okay, E2 and SN2. Nothing is changing here. But which one is going to be more than the other one? The temperature is high still. Temperature is still high. So it will still promote again the same thing. So the major product will still be promoted by the same thing. So we'll grab a hydrogen here. We'll break a bond. Then we're going to produce this guy. The minor product, that's just a difference. That's where the difference is going to go. So in the other one, that is going to happen by SN2. This guy will go and attach here. That will break off this bond. And look at the product that we form. We are going to have oxygen that has attached here. And then it is attached to another oxygen with a double bond. And then it has got a CH3 at the end. So this will be a product. Is that okay? It's a weak base, but it's a strong nucleophile. Do you understand the difference there? Should I repeat, or it's clear we proceed? Pardon? We still have this a strong nucleophile here. We still have a strong nucleophile, and the temperature is still high, and the nucleophile is not that bulky to be able to anyway, if it's supposed to be bulky, it actually, when you're comparing E2 and SN2, something that is bulky will promote E2, because for E we're actually grabbing something that is very far. Look at this, we are grabbing a hydrogen far, but for SN2 we are going to attach there, so there's going to be even a increased repulsion. I don't know if that makes sense. Okay. Okay, we also have these guys here. We have got R2 bromobutane by an hydroxide at 25 degrees Celsius. I love this one. Bromobutane, butane, four carbons, one, two, three, four. At position number two, we have got a bromine. Okay, and then now this is supposed to be R, meaning that we need to consider configuration. So already I know that my bromine is going to be the first group. This group here will be the second. So will be the third. Okay, a hydrogen is going to be the fourth group. So I'm counting from 1 to 2 to 3. This configuration is giving me R. So meaning that the bromine should be on a wedge. If I put it on a dash, it means that that will be the S configuration. So if you can't write this structure, it will be very bad because you'll not be able to get the right thing. Is that okay? Or should I repeat? Have we understood? Okay. Now I want someone to comment on the properties that we are using to determine what kind of mechanism we are going to have. Anyone? Yes. Yes, Doc. Hmm. SN2. Okay. Uh, i- is there another suggestion from anyone else? Is there another suggestion? Okay. Now, one thing that we need to know is that when we lower temperature, the reaction is going to go more with the S reactions instead of the E reactions. Okay. So the measure should be by SN. Now, so ever it is going to go, of course, it's supposed to be SN2, right? It's supposed to be SN2. But look at this. We are using hydroxide. Anyway, they've not given us a solution. We're using hydroxide. So there is also a chance of the reaction going not just by SN2 but also by SN1. Hope that is okay. There's also a chance that the reaction can go by SN1 instead of just by SN2. Why? When this thing which is here, when this guy loses this bromine, it is going to form a carbocation intermediate. So depending on the solution that we are using, this solution can actually stabilize the carbocation intermediate that we form. So the reaction will not prefer going by SN1 if, say, the solution we are using is aprotic. But if it is a protic solution, let's say you have got water, when we form a carbocation intermediate, that thing that we form is going to be stabilized, okay, by the water. So it will still be stable enough to undergo SN1. So secondary groups can also undergo the ones, and that will depend on the what on the property of the solution that you have. I don't know if this is okay. Okay, all right. But here we're expecting that the major product should be by SN2. Okay, SN2 because of the properties that we have. So this one will come and attack from this direction, and that is going to expel this guy. And look at what we are going to form. There is going to be a reversal of configuration. So what we were attacking was on a wedge. The product is going to be on a dash. It is very, very important to understand that for SN2. We can also form an alkene in this mechanism. So from where the Br is, we can come and grab the proton, sorry, can grab the proton either from here or from this end. But then the major will be when we grab a proton from this end. Because when we grab a proton from this end, we're going to form a primary carbocation, right? And that is not stable. Now, if the solution, if let's say if we knew what was in solution, say if they said we had water there, this reaction would best move by E1. We first lose the bromine. That is because we are going to form a carbocation intermediate, and that can be stabilized by water. But then I don't know the solution for here, so I cannot conclude. Okay, I cannot conclude really. It would be the same way with also if we had water here. This thing would have happened also by SN1. And what would have happened is that we would have lost that bromine. Could have formed a positive charge here. And then the next thing that would have happened is that the hydroxide would have come in. Now the hydroxide would have attacked from the front or it would have attacked from the back. Meaning that had it been like that, we would have had two possible products. We could have formed this. We could have formed also where it is on a wedge, like that, hydroxide. So those would be the chances. I hope it is okay. Okay, so that would have happened. Now let's go on with the product we are talking about that is forming by elimination. So by elimination, we are saying we are going to grab a proton. Hydroxide is going to come in and grab a proton from here. That will break the bond and release our product. And this is going to be the product that we are going to have. Is this okay? Then for the last one, for this one, hope is we are talking about SA3 bromomethylhexane. This is hexane. So 1, 2, 3, 4, 5, 6. Position number 3, we have got a methyl. Position number 3, we have got also a bromine. So here, supposed to have, okay, let me write it this side. Supposed to have a methyl. Let me say I put methyl on top, CH3, and then I put a bromine. So definitely if I put it like this, then bromine will be number 1. This group this side will be number 2. This one will be number 3. So look at this. We are moving from 1 to 2 to 3. This is supposed to be R. But then I want my compound to be S. So meaning that I need to change my group 1 should be at the back. My group 3, my group 4, because this will be the fourth group, should be in front. Such that if it is in front, then when we are naming configuration, this will no longer be R, it will be S. Every time the fourth group is not at the back, we reverse configuration. So I'm going to put a methyl in front, like that. Then the bromine is going to be at the back. I want someone also to comment on these properties. The substrate, the temperature, the base. Anyone? Anyone? E1. Okay. Okay. Thank you very much. Is there any other suggestion? Okay. The base that we have is an hydroxide. Hydroxide is a very strong base. It's also a very good nucleophile. Remember, it's coming from water. Water is a weak acid. So when you form hydroxide, it's a strong acid. Sure, sure. Okay, this is methanol. The compound down is methanol. So I also was saying water. So this is not. So supposed to have methanol. Okay, methanol there. So now when alcohols are attacking, the oxygen does not participate in. Okay, so it's supposed to be like so. That's our methanol. Okay. So methanol is not a bad nucleophile. It's actually good because of the oxygen. You can lose that hydrogen, it will be good. But if it is in this form, it is much stronger than when it has got a hydrogen. Things which have a negative charge, become more stronger. Because this is a tertiary substrate, it means that the reaction will not be able to happen by SN2. Because the temperature is low, there is chance of having SN1. Okay, there is chance of having SN1. Because the base is not very much substituted, there is more chance of the reaction going by E1. So when this thing first leaves, and then we'll be able to go and grab a proton. So does that mean that if it is more bulky, then it will happen? Actually, when it is very much bulky, it was supposed to happen more by E1 because you are grabbing after this group has already left. But generally, what we are saying is this: when you have got something that is tertiary, there's going to be a competition between E1 and the SN1. If the temperature was high, the SN1 wouldn't be there. So SN1 is like a very, 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 very minor product. But these guys like going by one. The reason for that is because they form stable carbocations. So the bromine will be able to leave. The product that you are going to have will be this. Now, if the bromine leaves, you don't show configuration because this carbon will now be only bonded to three things. Okay, for three things you don't have chilarity there. So this guy can go by E1. So by E1, the major product will grab a hydrogen from this end. Okay, instead of grabbing a hydrogen from here, you always grab a hydrogen better from the group that is more substituted. So it will be grabbed, the bond here breaks like that, and would have formed our double bond. So I've got a methyl at this point. We have our double bond. This will be the major product. We can have again a minor product that is going to come when we put the double bond at the other position. One, two, three, four, five. So I'm writing five carbons. We're supposed to have six. One, two, three, four, five, six. There's a methyl here. So I could have also put the double bond. Okay, I could have also grabbed the hydrogen here. So I wasn't seeing, I forgot that, so I thought that was primary. So you can also grab this hydrogen. The bond will still break and then form a double bond here. So these two guys are equally stable. So these are the major products. Minor product will come now by SN1. So the same thing that we add there, There's a methyl here, the positive charge. Now our alcohol can come in OH and then it's bonded to CH3. This guy can come in and attack here. But then when it attacks, there are two possibilities. It can attack from the front or it can attack from the behind. So I've got a methyl here. So I'll maintain the methyl on a wedge. So meaning that your group can come here. Remember it has hydrogen and the CH3. This will be positively charged. In the second reaction, water can come in and grab this proton, breaking this bond. Now you might ask, where is water coming from? All reactions happen in water. So that is how we're going to end up forming our ether. Another possible ether that we can form is we have got this, but then the alcohol will come and attack from the front. So what will happen is that it is going to be on a wedge or bonded to CH3. Remember, first it is going to be all bonded to CH3 and hydrogen. We'll grab the hydrogen. And then now the methyl is going to be at the back. So these will be the minor products. Is this okay? Okay, don't worry. You go through it and understand. But if you go through you don't understand, I'm here and we are here. Okay, so let's look at this one. We have got a Br. We have got that. Look at what we are using: sodium bonded to OCH3. Now this is a very strong nucleophile. Okay, a very strong nucleophile, OCH3, like that. It was more the same with the previous one. It's just that we were using the same our solution as a nucleophile. So this one will more happen by the one. So the bromine will first leave. We'll form our carbocation. Now this guy can come and grab. They've not even showed temperature here. Okay. So this guy can come and grab a proton at different ends. The positive charge has formed here. We can remove a proton here. If we remove a proton here, this bond will break. The product you are going to have is this. If I remove a proton from this side, the proton I'm going to form is going to be the same as the one which is here. I mean, the compound I will form is the one which is here. If the double bond forms here, it's the same, it's not different. So don't get confused on that one. The other thing that I can do is I can grab the hydrogen at this end because the positive charge is here. Remember, I'm moving just one step away from where the positive charge is. If I grab this hydrogen, double bond will come and break and form here. So I can also have this as a product. My product can also form by SN1. But by SN1, we'll simply go and attach where the positive charge is. We can either attack from the front or from the back. If we attack from the front, if we want to show stereochemistry, methyl is going to be like that. Then your incoming group is going to be like so. If you attack from the other side that you didn't attack in the first step, your methyl might be like that, and then your other group is going to be like so. So these will be your possible products. Question is, which one is going to be the major product? Major is always by E. Okay, so this will be by E1, major products. The minor is going to be down here. Is this okay? So, okay, so that is that. Now let me just have another look here. And I didn't pay attention to the nucleophile we are using. We are using a strong nucleophile. Strong nucleophiles prefer, sorry, I'm pointing down. Strong nucleophiles prefer substitution, right? So that will be more by. So the major product we're expecting is by here. It's a strong nucleophile and it is not hindered. Now, when we hinder the nucleophile, we are going to be able to change. The major product will be by E. Actually, we will not have any substitution reaction. We will not have any substitution reactions. Take note of that. We will not have any substitution reactions. So what is going to happen is this. The bromine in the first step is going to leave. Now, this group, the potassium doesn't affect anything in the reaction. Take note of that. So this is O minus. This guy is too bad to go and attach, even if it is by SN1. So that product will not form. So here will only have one product. There's not going to be any major or any minor. Actually, the major and minor is going to be there. If we grab the hydrogen here, but they are all going to be by elimination. The bond is going to break. So we're going to form a double bond here. This will be the major product. Can also grab a hydrogen at this end. When you grab this hydrogen, this bond will break. Okay. And that is going to be a double bond here. That will be a minor. So both the major and minor products are coming by the same mechanism. So there is no any substitution here because of the bulkness of the base and the bulkness of the substrate. Please, you are free to ask if there's something wrong at any point. Is that okay? Yes, please, Doc. This one is a solvent. So this one is a solvent. So this guy is the one to come and stabilize this carbocation that we can see here to be stabilized by the solvent because it's a polar solvent and polar solvents prefer or support formation of carbocations. Is that okay? Okay. Now we have this one. I think we did look at this one. Yeah, we did look at it. Provide a synthetic plan on how the following transformation can be carried out in good yield. In good yields, more than one step is required. Show all steps clearly, including the intermediates. No mechanism is required. If you remember what we did about this one, what was the first thing that we did? What did we do? Anyone that remembers? So the first thing involves the removal of the bromines. How do you remove the bromines? Hmm. Are we revising after we? Okay, I'm just Do we have anyone who attended the class when we did this? So that I know, so that I don't blame innocent people. Anyone who attended? Anyone? Okay, in the first reaction, you are going to use the zinc. Okay, you are going to use zinc. And what zinc does is that it does remove these two bromines that we're able to see here, to remove them both. And then to be able to attach a proton at one end. We actually form a double bond when we react with zinc here. And we said this was a that was what dihalide is. The word I do forget it. So I said the double bond actually does form here. Okay, like that. Let people are too quiet. Say something. Are we here? Okay. So when we form the double bond, is that a hand? Is that a hand or not? Okay. So in the second reaction, how do you think how can you convert an alkene into an alcohol by reacting with an acid? So that is known as acid catalyzed hydration. Acid catalyzed the hydration. So we're going to have our acid here, sulfuric acid, and also water. So acid catalyzed hydration of water. Now in this mechanism, what is going to happen is that your water, okay, your water is going to be able to attack. This thing has got a positive charge there. Now, before the water even attacks, before the water attacks, we are supposed to form first a carbocation intermediate. Carbocation intermediate. So what happens is that the double bond is going to act as a nucleophile. Double bond acting as a nucleophile to be able to grab a proton from the acid. When we get that proton, the next thing that happens is we are going to remember. So this end will grab a proton from the acid. Remember, if this is the end that has grabbed the proton, a positive charge will form over the other side. And when that happens, the next thing really is going to be water now goes and attacks where the positive charge is going to form. So the positive charge will form at this other end. So water will go on and then attack at that end. It will initially be like so, meant to be positively charged. And then we are going to use one other water molecule to grab a proton. Now you need to know that the first hydrogen actually there's going to be the, there's going to be yes please. That is very important. Thank you very much for that. So why is the positive charge forming on the tertiary and not on the secondary actually and not on the tertiary? I even used the wrong reactant here. If we use sulfuric acid and water, what we need to know this, if you use those two guys, water will come and attach here. Water always attach where it's more substituted. Now if we want it to happen the other way around, we need to react with BH3. Do you remember the mechanism with BH3? Okay. I just want someone to describe just a bit, not going into details. What happens when you're reacting an alkene with BH3? So I've discarded using water because the OH will not come and attach here. It will go and attach at the other point. Yes. Okay. So what you are going to use is BH3 with like an hydroxide, and this is going to happen also in the presence of like sulfuric acid. So the hydrogen acts as an hydride. So from BH3 we are going to have a hydrogen. Now that hydrogen is not hydrogen molecule that we know, a proton. This is an hydride. This guy goes and it will always go and attach where there is a greater substitution. So this reaction we use it in tetrahydrofuran. So the hydrogen will go and attach here. The intermediate that we are going to form, okay, there's no need of an intermediate here. And then the hydroxide is going to come and attach at this end. So they always happen opposite in opposite directions. The other thing that you need to know is that these ones happen by what is known as a sign. Okay, sign. When the hydride attached in front, the hydroxide will also attach in front. That is what happens. Please take note the mechanism of BH3 is very important to prepare things like this because this wasn't supposed to be formed. The OH was supposed to come and attach here. So you should know why as it. So the question which the dog asks was very important. So that is what happens for you to be able to form the product that you have. Is that okay? Okay. Please do revisit if you can no longer remember how to use this. Do revisit the tutorial before the time finishes. Okay, we have got this. Predict the product of each of the given reactions below. Also give a detailed mechanism. Hmm. We have got this. The first reactant here is mercuric acetate in tetrahydrofuran. We can already see the reactant, so I'll not write them. We'll just go direct into the mechanism. Anyone to help us? We really talked about this mechanism. We really talked about this mechanism. What happens in this mechanism? Anyone who can remember? So what I saw was if someone is speaking, it seems too easy such that we also get it for granted. But we don't even go through it and we end up forgetting. So that's not good. Anyone who can remember what happens in this mechanism? Just the first step. We can't. Yes, we did it. Mm. We don't. Yeah, yes, doc. Okay, you should go to. I think should be the last video that we did, if not second from last, on alcohols. Do we remember oxymaturation, dematuration? Yes. Okay. All right. So let's proceed. So this is known as oxymaturation. denaturation, and we did talk about it. So the first thing that we have is that okay, I'm going to write it in steps because look at the marks. In step 1, we get our mercuric acetate. Okay, we are going to get our mercuric acetate. Let me get it as HgAcO2. We had to explain to say that for this mercuric acetate, one acetate is going to go. We remain with the one acetate bond to the mercury. So it remains like so. And then we are going to have the acetate. The acetate here is going to be negatively charged. The mercury has got fewer bonds, is going to be positively charged. In step 2 now, our double bond is going to come in. It will act with this guy which is positively charged. The double bond will be able to attack. Now, one important thing that we said was oxymercuration denaturation is going to go by Markov-Nikov's rule. This bigger group will attach at the less substituted compound, but hydroxide, because in these reactions we are actually forming, we'll be able to form alcohols. So the hydroxide is going to attach on the more substituted carbon. So that's why this group attaches on the less substituted carbon. But then as this one is attacking, it also a bit attacks back. So the intermediate that you are going to form is going to be like this. This thing is attaching at the end, mercuric acetate. So there will be an attraction that will form because there's going to be a positive charge here because we are breaking the bond, right? We are breaking that bond as we are forming, as this HAC is attaching. So because of that positive charge, there's a bit of attraction there. But I'll not show the charge there because it will remain as a partial charge because of this small bond that is forming. And then in the next reaction now, your water is going to come in. That will be step 3. Look, water is, we have got water here. We also have water on top there. So that water is now going to come in. Okay. Just the water that is on top there is going to come in. Now water always attach or attack where there is more substitution. So it will come and attack here. And that will break fully this bond which was formed partially at this point. Are we okay so far? Okay. Now in the next step, we don't want to have that oxygen. That is the one to make the compound neutral. So we're going to use another water molecule to come and remove this proton. So this will be the end after we have used what is on top. Now we can use what is down. So from what is down, we are just getting that's sodium borohydride. So we're using an hydride from there. This hydride comes by SN2, attacks here. It displaces this group. So the final product will be like this. This will be our product. Hydrogen has attached there, so we know that we don't show hydrogen, isn't it? So that is our product there. Is that okay? Okay, so Water comes in, grabs a proton, we form our hydroxide. Now it's time to remove this mercuric acetate. And we use an hydride that is coming from the sodium borohydride here. So the hydride is a nucleophile. This nucleophile can go and attack where there is this the carbon that is holding the mercuric acetate, and that breaks the bond with the mercuric acetate the hydride has attached. I don't know if it's okay now. Okay. Okay. If there's no other question, let's answer the next one here. Now, here we are reacting water with, alcohol with PCC. Can someone help us? If we talk about PCC, what is PCC? What does it convert water to? That is the first thing to understand. Anyone? So PCC is an oxidizing agent. It will convert primary alcohols into, okay, primary alcohols are going to go into aldehydes. Secondary alcohols into ketones. Things like potassium permanganate and then what's that? This one, chromic acid. These ones are stronger oxidizing agents. They convert primary alcohols into a carboxylic acid. So you can see what we have here is a primary alcohol. So meaning we are going to convert this primary alcohol into a ketone, sorry, an aldehyde. So in the first step, you need to understand the structure for PCC. If you just miss the structure for PCC, or not even mark your mechanism, it will just start from here, everything becomes wrong. So PCC is like chromic acid. Okay, Cr, double bonded to oxygen, double bonded to oxygen, and then you have got a chlorine which is bonded to OH. That is one reactant, that is one component of PCC, and then you have got pyridine. So this is our PCC. Please don't forget, it has two bonds, double bonds with oxygen. One with hydroxide, the other one with, because normally sulfuric acid this was supposed to be OH, but you are just removing one OH from sulfuric acid, substitute with chlorine. So what happens that this nitrogen in step one will grab this hydrogen. The bond is going to be able to break here. And then now I've got oxygen that is negatively charged. Are we okay? We are good. We are going together. Don't forget, pyridine is going to carry. Yes, please. Yes, this is PCC is actually pyridium chlorochromate. So even from the name, you can see there is the pyridine there. Okay. So okay. So this is dimethyl chloride. It's a dimethyl chloride there. Okay, sure. So the next thing that will come in now, our alcohol is going to come in. The alcohol is going to act as a nucleophile. Oxygen will come and attack the CR here. When it attacks the CR, one bond is going to break off. Okay, that is what happens. So this guy will basically come and attach here. I've got CR. This becomes a single bond. And then we also have a double bond with oxygen. Don't forget that. We also have a chlorine. We also have another single bond with oxygen. Single bonds have a negative charge. Now in the next step, what happens is that the double bond is going to come back. One double bond will be able to come back. So this one is going to come down. When that happens, the chlorine is going to leave. Okay. Sorry, this one is going to be positively charged here. Oxygen bonded to three things is positively charged. Are we okay up to this point? Are we okay? So the next thing that will happen is that the proton here will be grabbed by this one oxygen. Now this should be this should come early. We need first to grab the proton. So one oxygen grabs the proton, this bond breaks. So when you are writing, that should come early. I forgot that. Before the chlorine can leave, that should come early. So we have now a double bond with oxygen. Let me put double bond with oxygen here, and then you have got OH here. Remember, we had lost our chlorine at one step. So what will happen is that now we will come and grab an alpha hydrogen. This hydrogen that is bonded to the oxygen, okay, will come and grab that hydrogen using the chlorine. When we grab this hydrogen, this will form a double bond here. When that happens, this will break off this group. So this is what we are going to end up with. Have a double bond with the oxygen. So this is how we form our aldehyde at the end. Is this okay? Write the structure of the alkenes that would yield the following carbonyl compounds when treated with ozone and with dimethyl sulfide. So basically what you do is just write this for the first one, write it like so. And also this other one, write the like so. You have got this methyl here, you have got the other one here, but then it's bonded like so. I'm removing the oxygens there, and then just connect there. So just connect it like that. So this is the compound that we have to break down. For this other one also, just try to round it. Look at how many carbons it has. 1, 2, 3, 4, 5, 6, and 7. So where there's the oxygen at 6, remove the oxygen. At 1, remove the oxygen. So 1 and 6 are supposed to attach. So there's a double bond between 1 and 6. So let's say this is a double bond. This is 1. This is the 6. The only way there can be a double bond between 1 and 6 is if these guys are in a ring. So 1 and 6 should be 2. It should be 3. It should be 4. It should be 5. And that should be 6. And then at position number 6, remember also have a Matthew at this end. So it should be a Matthew here. So this is the thing that we had to break down. Does this make sense? Give a simple test to distinguish between the following compounds: N-butano and 2-butano. So we already answered these. These are just from the tutorial sheet. N-butano is this one, two, three, four, five, six. Then you have got OH at the end. This is N. Now T-butano, this is tet butano. Okay. Tet is sorry, I've written, I was thinking of hexano, any hexano. So that's 4 carbons. It's a butano. One, two, three, four. And then you put now OH there. Now tet-butano, 4 carbons, but you should make a T. One, two, three. The fourth one is here. Put OH here. This is T. N1. What simple test can we perform with these two guys? We already answered this in the previous class. Anyone? So T cannot undergo oxidation. So it's good you also name the reagents. Remember, this is 6 marks. So oxidation of this primary alcohol with PCC is going to give you an aldehyde. Oxidation of this same primary alcohol with either this is chromic acid or hydrogen peroxide, potassium permanganate or sodium permanganate. These guys are going to give you a carboxylic acid. But then tertiary alcohols do not undergo oxidation. So that is a very simple test. And you just explain like that, you get the marks. So that was the end of this paper.